All right, let's dive into one of the most vital, life-saving patterns in all of distributed systems. This isn't just some abstract theory. This is the invisible pulse that keeps massive, complex systems from collapsing.
So remember day 4, we were feeling pretty good about ourselves. We achieved horizontal scaling, spinning up 1,000 servers to handle just about any load we could throw at it. Our system felt, well, it felt invincible. But we kind of left one terrifying question just hanging in the air.
I'm not talking about a big dramatic explosion. I'm talking about a silent failure. The lights are on, but nobody's home. How does the rest of the system, all 999 other nodes, even know that one of its own has just vanished? This is the kind of ghost in the machine that keeps system engineers up at night.
Okay, so the first idea that probably pops into your head is the most obvious one, right? Let's just watch them. Let's post a guard.
It seems so simple, doesn't it? We'll just have one dedicated server, let's call it the Watcher, and its only job is to go around and knock on every single door. Hey, you alive? Yep, cool. You alive? Yep, good. It just asks every single server one by one if it's okay. I mean, what could possibly go wrong?
Well, here's the problem. This all-to-all communication, this centralized check, creates a massive bottleneck. Every single node has to talk back to the Watcher, and our poor Watcher has to ping every single node. At a small scale, maybe this works. But we're not here to build small systems, are we?
So let's up the stakes. Forget 1,000 servers. Let's imagine 10,000. Now our Watcher has to send and receive 10,000 messages over and over and over just to check for a pulse.
And here's the punchline. The Watcher becomes its own worst enemy. The very system we built to detect failure ends up creating a massive, self-inflicted, distributed denial of service attack. It just gets so overwhelmed by requests that it grinds to a halt. It's a classic, epic failure mode. We need a smarter way.
So this brings us from a single, frazzled Watcher to a self-aware, living system. Instead of one server frantically asking, "Are you alive?" what if every server just announced its presence? And this is the heartbeat. It's such an elegant, powerful idea. Each node, on its own schedule, just sends out this tiny, lightweight message. It's not a question, it's a statement. It's just saying, "I'm here, I'm still working." To really get a feel for this, let's build a picture in our heads. I want you to imagine a vast, dark space, and in it is a grid of 1,000 perfect, glowing blue cubes. Each cube is one of our servers. They're all busy, all processing requests. And now, just watch. From the very center of each of those cubes, every 3 seconds, a soft green pulse of light just emanates out and then fades. It's rhythmic. The entire grid is pulsing together. It looks less like a machine and more like a single giant breathing organism. This is our healthy system. But a pulse is totally useless unless someone notices when it stops. So the system needs a rule. It needs an agreement. And that rule is the timeout. And it has to be absolutely merciless. Because if it's too short, you risk declaring healthy nodes dead during a tiny network blip. But if it's too long, your system is way too slow to react to real failures. And there it is, a sudden break in the rhythm. Deep inside that grid, one of our blue cubes, it just went dark. Its little green pulse is gone. The pattern is broken. The rest of the organism has to notice. The countdown begins. A red timer appears right over the dark cube. 3. Is it just a temporary network blip? A moment of slowness? The system waits. 2. But it can't wait forever. The health of the whole system is more important than any one part. 1. So here's what's actually happening under the hood. Each node, like S0 right here, keeps this little membership list of its neighbors. It tracks their ID and this heartbeat counter. Now, look at node S2. See how its counter hasn't been updated? It's stale. The timeout has expired. So, at this exact moment, S0 marks S2 as suspected dead. And that's it. The verdict is in. The system declares the node offline. And instantly, all incoming traffic that was headed for that dark cube gets ruthlessly rerouted to its healthy neighbors. The system just amputated the failed part to save the whole. It healed itself. This feels like a perfect solution, right? But in distributed systems, every solution introduces a new and usually more subtle problem. We've just assumed that the silent node is dead. But what if it isn't? Really think about this for a second. The server inside that dark cube could be running perfectly fine. The CPU is humming along, memory is clear, everything's great.
but the network connection got severed. It's trying to send out its heartbeat, but the messages are just dropping into the void. It has no way to tell the outside world it's okay. This quote from Designing Data-Intensive Applications just captures this nightmare scenario perfectly. From the perspective of the rest of the system, that node is dead. They've already held the funeral and moved on. But the node itself is totally fine, just screaming into a vacuum that nobody can hear. This is called a network partition, and it is one of the hardest problems in distributed computing.
So here's the absolute crucial point. The system can't tell the difference between these two states. Has the node truly crashed and burned to permanent failure? Or is it just temporarily isolated by a network fault, a partition? To the outside observers who are just listening for a heartbeat, silence is silence. And that ambiguity is what makes building these reliable systems so incredibly challenging.
Okay, so we've built a system that can detect silence and heal itself. That is a massive leap forward. But what comes next?
So look at what we did. Our system can now heal itself. But what if the nodes don't just want to say, I'm alive? What if they need to share complex secrets with the entire cluster? For that, well, they need to learn how to gossip. Tomorrow, on day 19, we're going to learn the gossip protocol. Be sure to follow along.